Okay, so here is the example that I didn't finish. In class, we did all the statics, and then I didn't do the factor of safety part. So let's do that. So we have this rigid beam, AB. It has this linear distributed load. It's supported by single shear at A and a double shear connected at B, connecting to F1. F1 is a 2-force member. And then we have member 1 is then connected at support C, which also has a double shear pin connection. And then it gives us dimensions. So let's start with part A. We're given a yield strength, so that's just a yield stress, 340 megapascals. We have a factor of safety of 1.67. When we see these two things, we know we're going to take our yield stress of 340, divide it by our factor of safety of 1.67, so that we get an allowable stress. That's going to be the allowable normal stress of member 1. We know the force in member 1 from all the statics we did. So then we're going to find the minimum cross-sectional area for member 1. Okay, so we did all of this statics. So we drew our free body diagram. We drew the linear distributed load, turned it into a resultant load. We found the angle that F1 is working at. So we drew F1 in, we broke it up into components. We took a moment around B so that we had this resultant force, positive moment, and then we had our AY, negative moment, solve for AY. Some of the forces in the Y, we have the Y component here of F1. That gave us the magnitude of F1. Then we took that magnitude, multiplied it by the cosine of theta. That gave us how much of F1 is going in the x direction. And then we had the force AX. Since we're working on a pin, we're going to need the resultant force acting on the pin. So we took the square root of the sum of the squares of ax squared plus ay squared and got a resultant A force. Okay, so we did so much statics. It was great. Now we're going to do the mechanics of materials part. So minimum area for bar 1. So we know, first thing we talked about, we have to calculate sigma, the allowable stress. Sigma allow equals sigma yield given over the factor of safety given. So this equals 340 megapascals all over 1.67, and we get 203.59 megapascals. This is our allowable stress, so that's what we'll be using. So then to find the minimum area, we go back to our stress equation, and it's going to be sigma allow equals F1 over the area. We know F1, we know sigma allow, so we can solve for the minimum area. So we're going to call this A min. A min is greater than or equal to F1 over sigma allow. And that equals, in newtons, F1 is 21,261 newtons all over the allowable stress of 203.59 newtons per millimeter squared. And we get a minimum area of 104.4 millimeters squared. Answer for part A. Part B is a bit more work. It wants the minimum diameter if all the pins of A, B, and C are going to be the same size. So of A, B, and C. So we know that pin B and C, B is in double shear, C is in double shear. Ada's talking. They both have the force F1, CX and CY. The resultant force of that would just be F1. B feels F1. So they have double shear, the same force, so they're going to produce the same minimum pin diameter. But at A, we're in single shear, and we have a different force, so it's the resultant force of A. So we have to calculate the minimum diameter at A, and then the minimum diameter for pins B and C, compare them, and take the bigger of the two. Okay, so let's look at pin A. Well, first let's calculate the allowable shear stress. Tau allow. That's right, we didn't even read part B. So part B. We're given an ultimate strength, so it's just an ultimate stress of 270 megapascals. And a factor of safety of 2.5. So allowable stress is going to be the ultimate stress divided by the factor of safety. Then we use that allowable stress so that we can calculate these minimum pin diameters that can be used. And we want the same diameter for all three pins. Okay, here we go. So allowable stress equals ultimate shear stress over the factor of safety. That is 270 megapascals all over the factor of safety of 2.5, and we get an allowable shear stress of 108 megapascals. Okay, so now we're going to look at pin A, which is in single shear. And it has a force acting on it equal to this resultant force of A. So we use the allowable shear stress, tau allow equals V in this case is F1. No, sorry, is the magnitude of A all over, so that's a force, all over the area of pin A. So that means the minimum area for pin A equals the magnitude of the forces at A all over the allowable shear stress. So that is 15,873 newtons all over 108 newtons per millimeter squared. And the minimum area is 146.97 millimeters squared. They want the diameter, but we could just move on. Well, let's just calculate the diameter. So the minimum diameter of pin B then, area of pin A equals pi over 4 d of A squared. So we have d min at A equals 4 over pi times the area which is 146.97 millimeters squared, and it's the square root of that. So D for pin A is greater than or equal to 13.68 millimeters. Okay, now we have to find the minimum diameter for the pins at B and C. So, pins B and C, which are both in double shear, and both have the force F1 acting on them. So, we have, since they're in double shear, we're going to divide that F1 by 2 to account for double shear. So, because our equation is tau allow equals V over area of the pin, V in this case equals F1 over 2. So that is 21,261 newtons all over 2. V equals 10,630.6 newtons. Okay. So then we calculate the minimum area. A min pin BC is greater than or equal to the shear force all over the allowable shear stress, and that equals 10,630.6 newtons all over 108 newtons per millimeter squared. Newtons cancel, and we get 98.43 millimeters squared. That gives us a diameter for the pin at B and C is going to be greater than or equal to 4 over pi times that diameter, 98, or that area, 98.43 millimeters squared. Square root of that And we get the diameter equals 11.2 millimeters. That is smaller than for pin A. So that means the diameter of pin A controls. So the minimum diameter equals 13.68 millimeters. All right.